If you want a new generation of refined, high performance and cost viable general aviation aircraft, you have to have a cost-effective gas turbine engine. Now, nobody would sell us one, so we've had to build one ourselves. Yeah, there is a finite risk of developing a new turbine engine, but it's really nothing like the pioneers of the 50s and 60s faced. We already know how to make this work. There's lots of examples of how to make it work and how to make it reliable. We've got a team full of people that have done all of this before. All we have to do is cut out the middleman, make our own version, and then use modern manufacturing methods to make it better and cheaper than ever before. The cost of developing a new turbine engine is significant, but we can afford it. We've got approaching 1,500 orders, a further 3,000 to 5,000 in the sales pipeline, and we get to market fast by fielding HX50 before we field HC50. We've done with a small but amazing team what would have traditionally taken defence corporations or governments to do. And as a direct result of that, we've managed to build a new turbine engine at around 10% of the price of our nearest competitors. When you think about time, think about this. We've created a completely new aircraft business, and created our own market for our own engine. We designed every part and every process to make every part and every process to inspect every part from scratch, and then built all of the equipment to test those parts and all of the facilities you need to be able to do all of those things. Now, that kind of depth of capability, that kind of quality, that kind of control takes time. But now we stand on the brink of an unprecedented renaissance in general aviation. And that's all because of GT50. I think the time for talking is done, and now it's time to demonstrate. We're just a couple of months away from GT50 running for the first time. So now I think it's time for our work to do the talking. Good evening and welcome back to PC1 for the February AMA session. Tonight is a GT50 special as we draw ever closer now to the first run of the very first prototype GT50. Once we've covered developments from across the engine program, we'll cover some of the choice highlights from both the composite main rotor blade program and also the Digi Cockpit before finishing off with some questions as always. Now, GT50 comprises many complex parts made from the finest materials and processes. We're now coming to the end of the painstaking period of building the very first examples of each of these components. Tonight, we'll showcase what we've built and what really goes into a GT50 engine. Let's start with the compressor development. GT50's impeller wheel is manufactured from high-grade aerospace titanium alloy. The blanks have been carefully heat treated. The blades, the curvix, the labyrinth seals have all been precisely machined. They've passed our painstaking inspections to exacting standards and now can be assembled and balanced with the rest of the gas generator rotor. The next component in line is the vane diffuser. GT50's vane diffuser requires accurately machined diffusion passages and turning vanes, extremely tight tolerances to maintain a gas-tight seal, and extremely smooth surfaces within the vane passages themselves. In production, it'll be manufactured as a cast and then second stage machined assembly, which is then brazed together to create the gas-type seals. We've now completed the front and rear halves of the first two diffusers. It's passed all of the detailed inspections and we're ready to braze the two halves together for assembly. This is GT50's annular combustion liner. It's been updated based on the extensive combustion and fuel nozzle testing that we've been doing to include improved dilution and cooling holes, that's these fellas around here, an improved heat shield at the back of the combustion liner, and then an updated thermomechanical design to help it resist the thermal stresses that it'll see in service. We've got updated fuel nozzles and swirlers that we've reported to you previously, and we're now updating the roll forming and expanding tools to allow us to finish off the final version of that, which will go into the prototype engine. The material to allow us to do that is already in stock here at PC1, and we'll be producing the latest combustor over the coming weeks. In addition to the combustion liner refinements, we've also been updating the fuel system architecture. The system has now been updated for significantly improved performance. We've improved the pressure atomizing nozzles, and we've characterized those by extensive flow testing over on the flow rig. Combustion rig testing is ongoing, and we're using this to validate both the ignition capability and the flame stability of the engine throughout the operating range. The latest fuel nozzles, manifolds and swirlers are all in build at the moment, ready to be assembled with the prototype GT50 engine. The new fuel system architecture provides for both simplex and dual orifice pressure atomizing nozzles. When we're using simplex nozzles, we bring the nozzles on in groups of nozzles to control the ramp up of fuel rate, giving us the bandwidth we need for operating the engine across all of its operating conditions. Production and inspection methods for both types of nozzles are now stable, and we can produce these nozzles repeatably using our watchmaking equipment. Ignition, cross-lighting and combustion stability are now actively being tested and optimized on the combustion rig. One of the components that we suspected from the outset was going to be one of the more difficult items to manufacture was the high-pressure nozzle guide vane casting. This is a stationary row of blades that's cast in a single ring from superalloy material. I'm pleased to report that we're now reliably casting these rings defect-free right here in PC1 in the correct superalloy materials. The guys have done an excellent job at correcting for the shrinkage and deformations that occur during solidification in the casting process, and our inspection processes are now able to repeatably measure and quality control these castings. The cooling passages that we EDM in from the outside to allow air to flow through the vanes and then out through the trailing edge have now been developed and are working repeatably. And we've also improved the wax production processes to improve the surface finish that we get on the castings. That's a relatively early one that we're showing there in the slide. All of these elements have now come together to produce reliable, high quality nozzle guide vanes that are meeting the required quality standards and tolerances. The gas generator rotor is really an assembly of critical, high-speed rotating components. Seemingly innocuous features like Curvix couplings and labyrinth seals are absolutely crucial to every aspect of the function of the gas generator unit. Extremely precise manufacturing methods and inspection methods are required to deliver these components to the required tolerances to make sure that we can keep the shaft properly aligned, concentric and free from run out. The front stub shaft, intermediate stub shaft, rear stub shaft have all been manufactured and inspected now, and they all meet the tolerances necessary for us to be able to assemble and balance the gas generator rotor accurately, meaning that all of these components are now fit for engine use. The entire gas generator rotor is held together by a central tie bar. This tie bar is extremely highly loaded, as the gas generator rotor spins at up to 50,000 RPM, it expands radially and then as a consequence of that contracts axially. The tie bar must have sufficient pre-tension in it to still remain tight and hold all of those components together with the right clamping force even after the rotor has shrunk axially under the action of centrifugal load. For this reason, the tie bar is extremely highly loaded, and to make sure that the threads are physically strong enough both statically and in fatigue, we have to roll these threads rather than cutting them. All of those processes have now been perfected here at PC1, both the production of the shaft, the rolling of the threads, and all of the associated metrology and quality control operations. All of this is done in extremely high-grade superalloy material that is difficult to work with, and these components have now been manufactured, inspected, and are fit for use in the prototype GT50 engine. GT50's high-pressure turbine disc, the body, the curvic couplings, the labyrinth seals, and the fir tree root are all now routinely being manufactured to the required tolerances. Extensive development work has been done on the fir trees to manage both the profile tolerance and also the pitch tolerance as we index this round on the CNC machine. We've been refining the form tolerances and all of the tolerances that control the position of the fir tree roots, and are now routinely hitting all of the tolerances required to safely use this extremely highly loaded component in the prototype engine. In addition to that, all of the metallurgical tests on the fir tree root cutting have also now been carried out and passed. Given that we use an advanced EDM wire cutting process on these fir tree roots, we've been able to develop that process to the level that it now leaves no recast layer in there, giving us the parent metal properties we need to safely operate the turbine discs that have been cut in this way. In addition to that, we've got one subtle tweak to make to the small spring clips that retain the turbine blades within the disc to improve the fitment of the blades in there under assembly conditions. And then the turbine, the blade, and that whole assembly is ready for use in the prototype engine. Investment casting small gas turbine blades is not for kids. It's a difficult process, and we've now managed to pull all of the elements of that process together to produce GT50's cast turbine blades routinely and repeatably right here at PC1. In addition to that, the heat treatment processes that are necessary to take the raw cast blades and develop all of the mechanical properties that we need for use in the engine have also now been developed and qualified, and all of the metallurgical and mechanical tests on our cast turbine blades have been passed, demonstrating that we meet all of the mechanical requirements that we need to for safe operation in the engine. Our machining and grinding processes are hitting all of the required tolerances for the fir tree roots, the platforms, and the general geometric tolerances of the blade. And our inspection processes are validating all of these things robustly, in addition to the quality assurance techniques, ensuring that the blades are free from porosity and other inclusions or defects. We can now make turbine blades. The stub shafts, the impeller, the turbine disc and blades, the tie bar all come together to form the gas generator rotor, the heart of GT50. These prototype parts have been carefully inspected and assembled by the team and are now ready for balancing. Now, the last time we showed you this image, it was a render, and now we've actually completed the production of the very first GT50 gas generator rotor. You have the forward stub shaft, the compressor impeller, the intermediate stub shaft, the turbine disc and blades, the rear stub shaft, the tie bar, and then all of the assembly features that go with it. This component fully conforms to the design intent. It's all made out of the correct materials. It all conforms to the tolerances and the requirements that we need to run this in the engine. And this has now been packaged up and sent off for balancing so that it will run smoothly within the prototype engine. All high-speed rotating components that run within the gas turbine engine need to be very carefully balanced. And what that means is we have to essentially remove bits of mass that are causing the rotor to have a center of gravity that is not perfectly on the axis of rotation. So to do this, we essentially run the rotor at relatively slow speed so that the balancing equipment can measure the out of balance forces, so the eccentric forces that it generates when the CG is not on the axis, and also the moments, the wobble that the rotor can make if the mass distribution is not perfectly aligned along the axis, also along the axis of rotation also. Once we've done that, the mass correction and the position of the correction is determined by the balancing equipment. And then we use balancing land, so elements of removable mass that we've built into the back face of the compressor and both of the sides of the turbine disc. We can remove bits of material from these areas in order to balance the the rotor so it runs smoothly. Now, to give you an idea of what our target is here, we have to balance that 11 kilogram rotor so that we've got no more than 5 grams more than a millimeter off the axis of rotation. And that's an incredibly tight tolerance to be able to get this to run smoothly. So to give you an idea, that's about a pea-sized piece of plasticine that we're trying to balance to with something that's spinning round at 50,000 RPM. Now, what I can report is we took the first rotor down for balancing, and we've managed to successfully balance the very first rotor to within the tolerances that we need. And what that does is that indicates that all of these components that make up the gas generator rotor have been manufactured to tolerances that are good enough to make these things in production. So our curvic couplings that assemble the shaft all the way along, and the general accuracy with which these complex forms have been machined, inspected and controlled are all sufficient for a production gas turbine engine. As I've said in a number of these updates before, the performance of any gas turbine engine is extremely sensitive to the running clearances between the aerodynamic blades and the stationary casing. In terms of the HP turbine, our blade liner is the component that sits around the blade tips and is responsible for maintaining that tight clearance between the blade tips and the stationary components. This is a cast and machined component that's made from an exquisite superalloy material, and then it receives an abradable coating to protect the turbine blades in the event of a short-term transient rub. These blade liners are now being reliably cast right here at PC1, and the machining processes have all been developed to deliver these components to the really tight tolerances that we need to hit the blade clearances that we require for performance. Some refinement is required to hit the last few tolerances for some of the sealing features, but in general, both the casting, the machining, the grinding, all of those processes are working really nicely, and that's on track to be ready for the gas generator test 2. All the way down at the front of the engine, we have the inlet casing. This is the area where all of the engine accessories, the starter generator, the oil pump, the oil fuel heat exchanger, and then the air inlet are located, feeding air into the impeller at the front of the engine. This is a cast component that's cast and machined from a lightweight alloy. And it provides the primary structural load path for the front end of the engine as well as the accessory mountings. The first prototype casing that we're making here, rather than casting that here at PC1, we're actually using 3D metal printing for this component. And the reason for that is this, like a lot of the other exterior casings, has had a lot of additional bosses and features added to it to allow us to attach all of the experimental instrumentation that we need to for the engine to support the test and development process. So this is one of the last components that we've released and sent out to production, as it's relatively low risk, and we've just given ourselves the maximum amount of time to be able to stabilize the final instrumentation fit that we need to test the engine. As we move back from the engine inlet casing, we have the impeller shroud. Now, this curved surface here is the running surface that the centrifugal impeller sits in, and we have to maintain incredibly tight tip clearances between the impeller rotating at up to 49,911 RPM in really close proximity to this surface. This is an extremely precise and large flexible component that needs to be manufactured very carefully. In production, it'll be cast and machined, and it also has an abradable coating applied to this running surface, and that's in order to protect the engine from titanium fires in the event that we have a tip rub after a hard landing or other shock event that the engine might see in service. These components are fully manufactured, they've been inspected, and we've also applied the abradable linings to them. All that remains to do now is for the final abradable machining operation to be done. Now, we'll machine the first one of these to a nominal size for the first engine tests, but we may choose to adjust this profile as we go through testing to tighten up the tip clearances or modify the offsets of those tip clearances as we learn more about the running clearances throughout the operating range for the engine. The inlet shroud sits within the intermediate casing, which butts up and traps the diffuser against the combustor casing. We've also now manufactured the intermediate casing. This is again a cast and machined construction. It's been fully machined, fully inspected, and again, this component is now ready for engine test. The combustor casing connects the cold and the hot end of the engine and contains the combustion liner where the combustion process actually takes place. It provides flanges front and rear for carrying the main structural loads, and then bosses all the way around the perimeter of the engine for accepting the fuel manifolds, the fuel injectors and the swirlers, and also the pads for mounting the service pipes. For the prototype engine, we also have added weight. The first GT50 will use a 3D printed, metal 3D printed out of the same alloy combustor casing that allows us to very easily adapt those different features on to accept the instrumentation and the other equipment we need to do the first stages of the testing on the engine. This version that you can see here is a slightly older one. The new 3D printed case should be here now within a matter of weeks, ready for the first engine assembly. Moving back now into the hotter end of the engine, this is the interduct, and this routes the hot gas from the gas generator down to the inlet of the power turbine. Its primary structure, it routes services from the outside world into the center of the engine core. It's a cast superalloy construction in production. And again, in terms of the first prototype engine, because of the need to be able to route a lot of instrumentation into and out of the core of the engine, we've adapted this component and made a superalloy cast 3D printed version of this to enable us to include all of the instrumentation bosses to be able to get all of that stuff mounted on the engine quickly and efficiently. The prototype interduct is currently in build and is due with us imminently over the next few weeks. Let's head over to the engine build area now, and I'll show you what all of these components look like when they're laid out next to each other, ready to be assembled into a GT50 engine. So this elaborate collection of engineering jewelry is what a GT50 engine looks like when you lay it out piece by piece on a bench. Let's start from the front end of the engine, and I'll walk you all the way through what we've been building for you that goes together to form the very first prototype GT50. Over the course of last year, you saw us developing the starter generator unit. That sits here at the front of the engine. As we then move our way back, we've just introduced to you the inlet casing, which receives the air, mounts the starter generator system, and provides all of the drive components for it. As we then go into the inlet casing, the next component we see is the compressor inlet shroud. So the compressor wheel sits against this abradable coating here. We'll machine that back to precisely meet the rotor blade tips, leaving just the tiniest of gaps to keep that impeller running efficiently. The rest of the shroud is machined away to be as light as it can possibly be and keep the whole thing as stable and tightly toleranced as we can. The impeller shroud then sits in the intermediate casing. This component sits inside here, and then this flange at the back clamps the vane diffuser to hold the impeller wheel and the vane diffuser in very, very close alignment, making sure that the flow leaves the impeller very smoothly and passes without turbulence straight into those vane diffusion passages. If you then move further backwards here, we've got the very first GT50 impeller. This was the one we showed you a few weeks ago. It's one of the first ones it is the first one we manufactured. You can see the curvix on the front, you can see the curvix on the back, the balancing land that I was referring to earlier that we use to make sure that the CG of this component sits nicely on the axis of rotation, making it run smoothly at high speed. As the flow leaves the output channels of the centrifugal impeller, it then comes in to these vane diffusion passages where the remaining energy in the in velocity in the gas is then gradually slowed down, and the static pressure increases. About 50% of the pressure rise that we get in the engine happens in the impeller. The remaining 50% happens in these vane diffuser passages here. Once the flow reaches the end of these vane diffuser passages, it goes round the corner and into these turning vanes that then straighten the flow to flow uniformly axially into the combustor casing and then into the combustor lining. Now, in order to get flow to stay in these passages, the diffuser has a second part, and these two parts fit neatly together and then are brazed with very, very tight seals to make sure that the air can only possibly pass in between the vane diffuser passages and the turning vanes and not leak anywhere else. Let's pop that down for a second. This component here sits on the back of the vane diffuser here, and this essentially mounts the clamping structure for the internal core of the engine, the nozzle guide vanes, and all of the other stuff that lines up with the core. This is the combustion casing. So we mentioned this a few moments ago. This is the superalloy casing that receives the combustion liner. The fuel injectors arrive through each of these 12 ports. These additional ports provide the access for the service pipes that pump compressed air around the engine, and also the oil feeds and the oil scavenge lines to get that out and to service the bearings properly. And then within the combustion liner, within the combustion casing, we've got the combustion liner. And this is the complex, elaborate, fabricated superalloy liner that's designed to have extremely high resistance to hot corrosion as it sits at 900 to 1,000 degrees, containing the ferocious combustion processes that go on continuously within the GT50 engine. At the back of this liner, you can see the 12 injection ports. We have cast fuel manifolds that go in through the engine through, line this up properly, in through the engine through these ports here. And then the fuel nozzles sit in machined holes in the end of each of these manifolds. These are then clamped on the back of the liner with these spring clips here. Each of those fits in there and traps a floating washer to allow the liner to breathe in relation to the cooler combustion casing on the outside. What you can see on the inside of the combustion liner here is essentially the outlet port, so the hot gases come round that corner and then come back out this way via the nozzle guide vane, which was cast here as I showed you earlier. That sits in there and turns the flow so that it strikes the face of the gas generator turbine in the right orientation to make the disc spin. So we pointed out earlier that we'd been manufacturing HP turbine discs. So that's one of our HP turbine discs manufactured here in superalloy. You can see that it includes curvic couplings, labyrinth seals, fir tree roots, and a lot of very complicated features, all made from superalloy. That, along with its blades, runs within the blade liner. This is a cast superalloy ring that's then machined and ground down to incredibly tight tolerances. It'll receive an abradable lining that sits in between these metal lands here to give it some stability and support during operation. And this makes sure that the blades maintain their incredibly tight tip clearances to deliver the levels of performance and efficiency that we need to get the performance that we want out of the GT50 engine. The next component along here is then the rear bearing housing. So this is a cast component that receives the service pipes that come in from the outside world. It receives the gas generator bearings. It supports the rotating components within the structural casings and supplies the bearings with oil and then scavenges the oil air foam away from the bearings to keep them well serviced and nice and cool. This again is a component that's been cast here at PC1 and then will be finished machined, ready to receive its bearings and its service connections. On the back of the bearing housing, we have the bearing housing seal carrier. This is another small cast and then second stage machine component that essentially closes off the back of the gas generator bearing housing to seal in the oil and the secondary air system chambers as required. So a relatively simple component there. As you'll recall, the whole gas generator rotor is manufactured from a series of precision shafts. So this is the forward stub shaft. You can see the labyrinth seals, you can see the holes for the secondary air system, the curvic couplings, and then the female thread there that receives the forward end of the tie bar. And then we have the intermediate shaft, which is shown here on the rotor, and then the rear stub shaft, which much the same, curvic coupling, two-stepped labyrinth seals, and then the surfaces for the bearings to run on. That whole assembly is attached using the tie bar, and this really is little more than a glorified bolt. But it's a bolt that has a particularly hard job. This forward thread here has to go into the front of that stub shaft, and this thing then has to carry extremely high loads, because as the whole gas generator rotor spins at up to 50,000 RPM and wants to grow out radially, it wants to pull in axially. And to keep those curvic couplings together, to keep the rotor balanced, to keep it stable, we have to still clamp all of that sufficiently tightly against all the differential thermal expansion, against all of the transverse shrinkage that you get due to the centrifugal loads. And so this thing has to carry really, really high levels of pretension. To do that, as I mentioned to you earlier, we have to roll these threads rather than cutting them to give this thing sufficient strength and fatigue life. And then this thing sits in really, really close tolerance passages to keep the whole rotor together robustly as required. It's secured on the end with a locking nut and a locking assembly, and the whole thing is attached using a hydraulic puller to pull the bar, finger tight the nut, and then release it so that we've got a known pretension in that in every engine every time we build one. Then where we've got curvic couplings that go together, inside those joints, we have to make sure that the gaps between those teeth are properly sealed. And to do that, we produce these little spring clips that sit inside the shafts and then spring outwards to seal those gaps. And they're metallic because, of course, they have to survive at really, really high temperatures inside the engine. You can also then see here a high pressure turbine disc, as we've pointed out previously. So this is the superalloy disc, curvic couplings in the center. You can see the labyrinth seals on the outside, the female fir tree roots here, and some of the passageways here for the secondary air system to route air around the engine to keep the bore of this disc nice and cold, making sure it maintains its mechanical properties. And then here we've got high pressure turbine blades in the as cast and then finished state. So the blades are cast slightly longer than they need to be, with slightly bigger platforms, and then a lump where the root should be at the bottom. And then we go in and grind the fir tree root, grind the platforms, grind the tip to make sure we've got full control of all of the crucial dimensions that we need to have that work properly and to be able to be balanced properly within the engine. All of those things being successfully done here day to day at PC1. And then what we have here is the very first gas generator rotor. So this is just back from balancing, and what you can see here is the forward stub shaft connected to the compressor impeller, connected to the intermediate stub shaft, and then the high pressure turbine disc with all of its blades clipped into place, and then the tie bar and the locking nut assembly on the back of the rotor. You can see all of the labyrinth seals, the bearing faces on the front and back, and everything that goes into making the heart of GT50. Last year, you watched us develop GT50's Module 1, the starter generator and power management unit, building the prototypes, building the test rigs, carrying out the subsystems testing, optimizing the design, optimizing the production methodologies so that we were ready to start GT50. You also watched us build Module 4 of GT50, the speed reduction gearbox and drivetrain module, bringing together years of process development in gear design, bearing design, thin-walled flexible casing design, all to develop the very first version of GT50's drivetrain. On top of that, you watched us build the first high-speed test rig and commence testing on the engine's drivetrain. Next, we need to ensure that the prototype engine is fully instrumented to facilitate testing and development. To do this, the engine has to be adapted to include instrumentation bosses and the additional bracketry and cable management necessary to route the 100 different sensors needed to monitor every function of the engine that we're interested in during the development testing. Sensors are required for the safety and also to understand everything that's going on deep inside the engine as we run it through a wide range of operating conditions. This work has been successfully completed and many of the instrumentation parts are now here on site awaiting the first engine build. To complete the testing, we must be able to measure pressures, temperatures, proximity, speed, vibration, and a variety of other parameters. Routing the instrumentation throughout the complex labyrinth of passages within the core of the engine is extremely difficult, and sophisticated instrumentation bodies has needed to be designed along with lots of mounts and cable routing and management systems to ensure that we can route all of these instrumentation feeds into and out of the areas where they're needed, and that the instruments themselves can survive in the harsh environment inside a gas turbine engine. The raw instrumentation feeds are then brought back to our data acquisition system, which allows us to monitor and control every aspect of the engine's operation. To de-risk the gas generator test, as much testing is being done off-engine on simpler rigs as we possibly can. The fuel system test rig is being used to characterize the pressure atomizing nozzles. This allows us to look at the effects of different fuel types, fuel temperature, viscosity changes, and filtration standards on the overall performance and behavior of the nozzles. Minimum injection pressure for good atomization, and also the maximum pressure that the nozzles can be operated under is also being characterized so that we can set the fuel system up properly for optimum operation. We've been continuing the combustion testing while we've been building the gas generator unit. And we'll continue to do more of this on the run-up to first engine run. This allows us to further refine the pressure atomizers and their setup to optimize the injection pressure schedule throughout the range of operating conditions, particularly the critical ignition and run-up phases. It allows us to maximize ignition robustness, maximize cross-light robustness between the igniter plug injector locations and the other ones around the engine circumference. It allows us to maximize combustion stability across a range of operating conditions, and it also allows us to validate the very latest combustion liner performance and characteristics. Once we've built the gas generator, the engine testing will proceed in stages. The test rig provides all of the engine services, off-engine to start with, the fuel system, the lubrication system, the control system, and then all of the instrumentation that we've already introduced. The goal is to make this whole test rig as simple as possible, easing the process of development, but then make it scalable, so as we want to develop the testing, we're also able to do that. The test facility is now being developed. The container which will contain all of this is already here on site. A lot of the instrumentation and data acquisition systems are already on site. And our next job is to do the mechanical design and the mechanical integration of the test rig systems to take the gas generator unit over there and fit it within a test cell. So in terms of progress status, it's all good news. We are on track to complete the build of the gas generator by the end of April, as stated. The engine build and instrumentation will continue as soon as possible. So as components become available, they'll be built. We won't wait for everything. The gas generator rotor was successfully balanced last week, so one of the major risks, which is that of vibration, was substantially eliminated last week. We can make balanced rotors to run smoothly in this engine. The subsystem testing to de-risk the fuel system and the combustion system has continued throughout the build phase and will continue all the way up to full engine testing. As I've said, the instrumentation that's necessary is already here, and bought in long lead time items such as some of the high temperature metallic seals, the ignition components, and various other bits and pieces are already here on site, with a couple of outlier items that are on schedule to be here in time for first engine build. And the test rig is now in development. Okay, let's change track now and talk about our composite main rotor blade development program. So we've now manufactured 5 development main rotor blades, each one showing significant improvements over the last. Throughout the course of the development program, we've been refining the kitting processes and the plybook development so that the individual laminates are tailored perfectly to the exact shapes that they need to fit into within the mold and within the tooling environment. That's meant that the finished blades, when we section them and inspect them, have got the plies much more closely located to the design intent with each subsequent blade. The laminating procedures and the ply placement itself has also been substantially improved, making use of our laser alignment systems, and again, benefiting from the improvements in the ply book and the kit cutting, and also just generally getting better at making each of these blades as we've got more experience. We've done a lot of development on the curing cycle and the process parameters, playing around with the bag temperature for the internal mandrel bag to create the right levels of consolidation, the right levels of alignment of the wrapped mandrel that sits inside the blade. Each blade that's come out of the mold has been substantially better than the previous one, and the molded blade quality is now coming out as really quite good. The other thing that we've significantly improved, and we'll talk about this briefly in the testing in a second, is the part-to-part repeatability. Blades 4 and 5 have got very, very, very close mechanical properties to each other, and once we've finished sectioning them, we're expecting to find that the actual location of each of the plies within the part is exactly where we thought it'd be. In addition to the fundamental laminating processes, the bagging processes, the assembly processes that go into manufacturing and curing a blade, we've also now been developing all of the additional procedures that go into finishing a complete rotor blade section. So what you can see on the slide here is some of the downstream processes that we've been developing. We've done an extensive amount of work on blade surface preparation and then painting. We'll show you in a second, blade 5 has now got its erosion shields fitted, its root end bushings fitted, it's got the high conspicuity paint work on the top face, and then the low reflective paint work on the underside to prevent glare from the navigation and strobe lights. The root end bushings have received a lot of development work, both from the stress team upstairs, and then we've done the first trial fits of those down here on the shop floor. And then the remaining tasks that we've got to do from a pure practical manufacturing point of view is to get the trim wedges integrated, which is how we aerodynamically trim each subsequent blade. And then the balance pot integration, which is the location in which we put the trim weights to get the span-wise and the chord-wise balance of the blades right across every one that we manufacture. Let's go and take a quick look at blade 5 over in the demo area. This is HX50 development blade number 5, and it looks a little bit different from the last time you saw it, I bet. So as you can see, what we've done now is the blade has been fully painted with a fairly standard conspicuity paint scheme on the upper surface. This makes the aircraft easier to see in the air. It acts as a slight bird scaring factor as well, and it also keeps the heat from sunlight down to a minimum getting into the composite material. On the flip side, down here on the rear of the blade, you'll see that the underside of the blade, with the exception of the tip is painted in a matte black color, and this minimizes the reflection from your strobe lights, your navigation lights, and from any light reflected from the ground up on the blade, avoiding distractions during night flying. On top of that, we've now fitted the erosion shields all the way down the leading edge of the blade. These provide protection from erosion and other damage under all operating conditions. And then down at the root end here, you can see that the top hat bushes that we use to attach the blade pins and the blade fold mechanism are now also installed in the thick root end structure of the blade. The only thing that this blade is currently missing is we haven't yet fitted the trim wedges. So our blades don't have trim tabs, they use trim wedges, which modify the aerodynamic performance of the blades to get it to fly at the right height compared to its sister blades. And we haven't yet installed the structure here on the underside of the blade that receives the trim weights that allow us to balance the blade for a chord-wise and span-wise CG point of view. Aside from that, the blade is now complete in terms of all of the mechanical features that go in to manufacturing one of these blades. And what we've now got to do is continue refining the manufacturing process to get the consistency and the quality that we need for an airworthy blade, and then continue the development of the test program on these blades to get the dynamics tuned properly and the static and impact strength to where it needs to be for safe use on the aircraft. Helicopter rotor blades rely on a very delicate balance of the distribution of mass and stiffness along the length of the blade to get the dynamic characteristics that are necessary so that the blade doesn't experience unacceptable vibration and loads. Now, in order to do this, we have to ensure that every single ply that's been placed into each of the blades and then cured is exactly where the designer intended it to be and where the structural analyst analyzed it to be, to make sure that what we've designed and analyzed matches what we've got out there on the shop floor. Now, sadly, the only way to verify this practically is to do lots of cut-up trials on the early blades that we produce. So blades 1, 2 and 3 have all been subjected to dissection and then examination of exactly where the plies ended up in each of the blades, looking at the proper creation of the spar walls, of the plies that are used for bending and for longitudinal stiffness, the torsional wraps, and that these crucial structural shapes are formed properly in the blades, and that the fabrics that the composites are comprised of are orientated in the correct direction as per the design intent. Now, in the early blades, what we found was in the D-spar section, which is formed largely by a mandrel and then an internal pressurized bag, the combination of some small discrepancies in the kit sizing and the not quite balanced pressure in the vacuum bag around the mandrel meant that there was some wrinkling in some of these early plies. And so we've been adjusting the balance of those parameters and the makeup of the kit that goes into these components to get that tuned just right. And then in subsequent blades, we'll be doing further cut-up trials to make sure that we've got exactly the right composite in exactly the right place with all the fibers in exactly the right location to give us just the right balance of mass and stiffness that we need to tune the dynamics of these blades right and give you a really smooth and safe ride. The cut-up inspections allow us to accurately understand exactly where the fibers are within the blade and that we've developed the laminate that we wanted to at each span-wise location down the length of the blade. It's also equally important that we understand that we faithfully reproduce the external aerodynamic and structural profile of the blade to give both the aerodynamic performance and also the structural stiffness that we intended by design. In order to do that, we've used a full 3D external scan of the full blade topology. To do this, The metrology team have used a 3D laser scanning arm to create a full point cloud representation of the external surfaces of the blade, and then compared that with the 3D CAD definition from which the blade and the tooling was developed. What we found through a detailed analysis of this data is that the blades are actually really accurately manufactured. The tooling quality is really high. The aluminium tooling that we've made here gives good dimensional control over all areas of the blade, and we've just got a small nuanced area where the local expansion of the internal core materials are just leaving some pre-strain in the molded component, so when it's released from the mold it pops out a little bit. So a subtle amount of tuning of that pre-compression of the foam core, and we'll have a really accurate blade all the way across the span of the rotor. In addition to ensuring that we've actually got the composite material where we want it on the inside of the blade, and that we've accurately reproduced the geometry required on the outside of the blade, we also have to take into account the fact that when we're making these blades, unlike a lot of other processes, you're actually making the composite material at the same time as you're making the part by adding the resin to the carbon fibers in your own process. And for that reason, it's really important that we fully capture the characteristics of our composite materials, because they themselves need to be fed back into design, and we also need to ensure that we're producing consistent composite material with mechanical properties that are as good or better to what we assumed during the design process. Now, to that end, we have to do a range of composite material testing, starting with simple coupon tests and then moving up to subcomponent and full component testing across a wide range of mechanical loading scenarios. What you can see here is the first suite of coupon testing that we've done on both the blade, the suite of materials used for the blade composites and also for the airframe composites. The other factor that we have to take into account, which is of particular importance, is the fact that composite materials degrade significantly as they absorb atmospheric moisture and also experience elevated temperatures. So the design permissibles that we can use in designing both the blades and the airframe have to take into account this degradation, as well as damage resulting from mishandling during manufacturing or damage received in service. We have to make sure that the composite materials and the structural design of the blades is sufficiently robust to be able to deliver all of the required loading cases with all of this stuff taken into account. So what we've found so far from the coupon testing that we've been doing on our materials manufactured here with our processes and our tooling is that we're getting excellent performance for both the hot, the high, and the undamaged conditions of the material. So really pleased with the output from that testing to date. Now that we're starting to make consistent rotor blades from the in-house processes, it's time to start doing some preliminary structural tests on these blades. The first suite of testing that we've done is the static testing. So this looks at both static stiffness and also static strength. So what we've got here is a number of tests that look at the flap-wise and lag-wise stiffness and the torsional stiffness of the blade as a precursor to dynamic testing. These results are used to both qualify the analytical and the design methods that we use, and also to quantify the performance of the blade as molded here at PC1. So what we found when we compared the measured and the as-designed stiffnesses for blade 4 and 5 is that the values of stiffnesses for blades 4 and 5 were found to be within just 0.25% of each other. So for an early development stage blade, that's incredibly good. So we were really pleased with that. So we're already starting to see that the manufacturing process is demonstrating excellent repeatability. And so far we've found good agreement between the designed and measured results, though we've traced one minor discrepancy down to the fact that currently the blade is being moulded slightly over thick, and so the actual blade is slightly stiffer than the designed blade. So we'll be tweaking the manufacturing process to bring that into closer alignment and then repeating these tests on a subsequent manufactured blade. We've also now made a start on the 3-point bending tests to look at the structural strength of various sections of the rotor blade, and we're also starting to conduct some impact tests on both the faces of the blade and also the trailing edge to allow us to minimize the thickness of that trailing edge while still maintaining the required thickness for in-service robustness. In addition to static testing, blades 4 and 5 have also been subjected to dynamic testing, where we're using accelerometers to measure the natural frequencies at which the blade wants to vibrate and also the associated mode shapes. This is important because every rotor blade operates in a complex vortical wake which can readily excite modes of vibration and transmit high loads and vibration into the rotor system, the rotor hub, and the aircraft overall. To avoid this problem, we tune the natural frequencies of the main rotor blades to be well away from any frequencies at which it can be readily excited. So it's important that we prove that the rotor blades as built have got natural frequencies and mode shapes at the right spacing from all of the forcing functions that exist in the main rotor. In order to do this, we've set up a test down at the bottom end of the factory where we suspend the rotor blade from bungee cords, so it's not affected by the stiffness of the blade attachment or suspension system. And then we use what we call a bonk test to essentially simply knock the rotor blade, and then that impact energy readily excites all of the natural modes of vibration, and then that data can be captured through a series of accelerometers and the mode shapes and natural frequencies post-process to understand exactly where they are. Once we've done that, we're able to compare the measured and the as-designed values for both the mode shapes and the natural frequencies, and then we can take a view on whether they're close enough to what we intended or whether we need to modify the stiffness and mass distribution of the blade to make sure that we keep those frequencies adequately spaced from any frequency content that could excite vibration or generate high loads in the rotor system when it operates in practice. Moving on now to the development of the digital cockpit. All areas of the DigiCockpit are now progressing really rapidly. We now have a fully functioning version of the DigiCockpit software that's developed and is going through testing. The prototype integrated display processors have now been built and are awaiting testing up in the avionics lab, and the system integration with all of the standard peripheral devices that make up the digital cockpit system has been completed and is pending testing. We now have prototype hardware for the integrated display processor, which includes production grade touchscreens for the main screen and the IPI. That includes the underlying touchscreen, the backlighting box, all of the touch layer and the capacitive sensors and all of the coatings. We've got prototype mechanical casings, production connectors, all of the electronic hardware, the PCBs for the primary flight display, processor boards and the associated drivers, and the prototype avionics loom. All of these systems are currently undergoing testing up in the avionics lab with Eric. In addition to our hardware developed here at PC1, we're also doing all of the system integration with all of the external and peripheral devices that connect to or are controlled by the DigiCockpit. Both hardware and software aspects for all of the peripheral integration has now been developed, and detailed system integration testing is now going on for each of these units to ensure that they can be properly controlled and adequately communicated with. And in exciting news, we now have a fully featured version of the Hill DigiCockpit software that includes the following enhancements, which will be standard on all aircraft. All of the camera integration and controls are now present in the DigiCockpit. All of the screen control functionality is now implemented. Bluetooth music and phone integration is now implemented. All of the climate control integration is now implemented. The multifunction display functionality is now implemented. We've dramatically improved the IPI functionality. We've improved the autopilot functionality and also added all of the login functionality and much, much more. Let's go and join Eric and we'll do a live demo. So Eric, we now have a fully featured digital cockpit suite. Why don't you tell us about some of the latest features that you've added?
Sure, let's dig in. So starting with sort of the initial steps when you boot up the system, both big screens will take you right to their kind of primary pages. So on the primary flight display, it'll go right to the flight instruments.
Yeah.
On the IPI, it takes you to the login page. And so this is where you tie in your pilot profile to the system for insurance, logbook, all of that sort of digital record keeping type things. So if you have your Hill app logged in the system near the helicopter, then it will show your profile there that you can confirm and go straight through. If for some reason you don't have your phone nearby, then it'll show you previously configured accounts or users, and you can select one of those, type in your PIN, and it logs you in. So that is for the pilot profile management. You can also add a profile for the left-hand seat if you want to have multiple crew members connected to the system for record-keeping purposes.
That's great.
Let's go to the primary flight display. Now, a lot of the features here have been showcased already, but I wanted to show a few new features that have been fully baked in and integrated within the system. One of these is the camera background feature. We've shown some working prototypes of this now, but it's fully integrated within the architecture of the system. To turn on your camera background, as you see now, this is just the artificial horizon. To turn on the camera background, you can press this switch right there, which turns on the background feed. I can also do this through the IPI. If I just tap this screens button, it pops that up, and then I have the right display selected here in this tab, and I can toggle between camera background and artificial horizon. You'll see these switches here, which show the different camera options that I can use for that background feed.
Yeah.
Right now it's just the nose camera, but I can switch to the tail camera, which is a forward-facing camera mounted just under the tail rotor looking forward, so I can see the belly and the undercarriage. Or I can switch to the infrared camera feed. Similarly, I have this slider here where I can change basically change the contrast between the gauges and the camera feed. So if I want to darken the camera feed a little to make the gauges pop out a little bit more, I can adjust that with this slider here.
That looks incredible.
So that's the camera feed. The synthetic vision would also be another layer that once we have that finished, that would be something you could change using the screen control page to switch between artificial horizon camera feed or synthetic vision as your background layer.
Fabulous.
All right, let's go to some of the autopilot features next. So notice that I don't have any of the autopilot modes on right now, but I can select these either here on the PFD or using the IPI. So let's go ahead and just turn on the altitude mode. So if I turn that on here, you notice that the bug appears right there. Now, it always will just activate at whatever your current state is. So in terms of altitude, it's just going to turn on at whatever your altitude was when you enabled it. Similarly for heading, if I turn on heading, it will just put the heading bug right at your current heading. Now,
so it's never going to dart off to a
previous
datum.
That's right. It's always just going to hold whatever your current state is. Now, if I want to change those bugs, I can either, say for the heading, I can just tap that right here. And notice it starts pulsing there with a different color, and it opens up on the IPI this page where I can enter in either with the keypad or adjust with the puck what that new setting is. And you can see that it shows you your previous or your active bug position, and then it shows you what the new one is. And then I can either click confirm or just press down on the puck, and it sets that as my new setting. And then a similar sort of thing with the altitude bug as well.
So tap twist to set your heading, and then click.
Yeah,
or type
and
it in if
there's
you want
often
to.
two ways to go about this. So you can either kind of tap where it is on the PFD,
Yeah.
or there's also a button on the IPI to change that.
Really nice.
All right, let's talk a little bit about units. So we've shown some basic ability to change units, and this is, again, as is with a lot of these features, something that we've kind of partially shown before, but it's been fully brought into the architecture.
Yeah.
So for fuel, if I tap the fuel gauge here, it will cycle between percentage, kilograms, pounds, gallons, liters, and then back to percentage. And so you have all of those units available.
Yeah.
And then you have those unit selection options available for many other signals as well.
Yeah.
So if I go into the settings page and then click units, then see I have barometric pressure setting unit. So right now it's in hectopascals. So I can change that to inches of mercury. See here it's shown as inches of mercury. I can go back to hectopascals. And then for altitude, if I want feet or meters, and then fuel quantity as I've shown, temperature, distance, ground speed, all that sort of thing.
Fabulous.
Those are the main new features on the PFD. It's mainly just been integrating all of these things properly into the architecture.
Okay, so let's say we were changing either a pressure setting or a transponder code. We've got some shortcuts that you've developed out for those as well to get back to standard values, haven't we?
That's right. Yeah, so let's, for example, say we wanted to change our transponder setting. I can either go through the IPI, or if I just click this here on the PFD, notice that it highlights that and starts pulsing that it's kind of active in focus, and I can use the puck to edit that. As we've shown before, the new thing, as you highlighted, is, if I just confirm that and go back to it, we have these presets available. So you have your VFR preset for whatever region you're flying in. So in this case, 7000. So that just shows up here, and I can just tap that in to drop it in and confirm it. Similarly, as an even quicker way of doing it, if I press and hold the transponder button there, it'll just snap right onto that.
That's fabulous.
Similar story with pressure setting. You have your GPS. Basically, the computer determines what should be about the right QNH based off of your GPS altitude. So I can tap that to drop your GPS pressure setting right in there and confirm. Again, you can do the same thing just by tapping and holding the pressure setting button there on the IPI.
Fantastic.
Some other new things on the IPI that have been fully integrated within the system include your phone page, so all of your phone calls, contacts, etc. that get brought in if you have your phone connected via Bluetooth. So I've got that as well if you want just to enter in phone number on the keypad. And then your music, playback, similar sort of features you'd expect to see in a car infotainment system. Your climate control system, so temperature, fan speed, all that sort of thing. The screen control page, which we've shown already. And then settings. I showed some of the user management side of things. So again, you can select who the current pilot is in the system. You can set your display settings, screen brightness, day-night mode, that sort of thing. Units, and then pilot stations. So right now it's configured for the right-hand seat to be the pilot in command. But if you had the left-hand seat as your pilot in command, you can set that here, which basically swaps it over. And what that means is that whichever side is your pilot in command, it locks that screen, which is in front of that seat, to be the primary flight display.
Got it.
Bluetooth settings, as well as network settings for connecting to external networks, and also configuring the onboard Wi-Fi network in the helicopter. And then your EFB connectivity settings for managing your different apps for your EFB connections. Those are all the settings pages, and then we also have the intercom page, which is new, which has all the different settings for your different audio levels, and one page to control all of your different sort of audio panel settings, basically.
That's really neat.
Let's go to the MFD next.
Yeah.
So right now, you notice that we have we still have the left-hand seat being the PIC. Let's change that back. So right now it's in MFD mode, so we have sort of different widgets. We have the camera widget there with the camera view. I can make that full screen by tapping that here, and that maximizes the camera view to be full screen.
Yeah.
Again, you have all the different camera modes I can select either through those switches there or on the IPI, which camera is displayed on screen. So I can go to nose or the rear-facing camera, our IR camera. I can then, if I go back to normal there, can change those with the IPI or on the big screen. We have our music and our phone widgets, similar features as you have on the IPI, and then your climate control on the bottom bar.
Got it.
Now, the left-hand screen can also be the MFD as is shown now, or you can also have it be the primary flight display if you want to have both screens having all of the flight instruments on them.
Yeah, that's incredible. Looks great. Well done. It's taken a long time and a lot of determination to develop all of the knowledge, all of the capability, all of the infrastructure, all of the process knowledge to create all of the components necessary to build our own 500 horsepower gas turbine engine. But now, here we are, just 2 months away from being able to run GT50 for the very first time. Our incredible team have done an amazing job of producing almost all of the components now that we need to run that very first engine at the end of April into May. In addition to that, our composites team have done an incredible job at bringing together a whole suite of technologies necessary to produce efficient helicopter main rotor blades that have high aerodynamic performance, almost infinite life in terms of their fatigue capabilities, high robustness, and then to complete an extensive program of testing that demonstrates that the blades are doing exactly what we intended them to do. And we've now developed a fully featured version of our digital cockpit suite, including all of the software, all of the hardware, and all of the peripheral system integration. Thank you for your time, thank you for your attention. Now it's time for some questions.
Welcome back, everybody. It's incredible to have everybody joining from all over the world. We have thousands of people joining in here today, and it's great to have all of you. We're actually connecting from different parts of the world today. Ruben, I think we're covering all the different the areas. Ruben's connecting from South America. Today I'm in New Zealand, and yesterday I had the opportunity of visiting with one of our very, very early clients, actually serial number 5. It was incredible to be able to connect with owners all over the world. And Jason, of course, is at Production Center 1 over in the UK. And it really shows the global community that we have. We have connections from all countries, 78 countries in total. And it's really neat to be able to bring everybody together with this shared passion, which, of course, is the HX50. And Jason, wow, what an incredible update. I was just at the edge of my for the last hour and 15 minutes here, watching every detail that's going on. It's really coming together. It's so exciting to see the engine parts all now being finally manufactured and coming together and starting to assemble and on the test benches. And I get excited for every part of the helicopter. And I think the very end actually got the biggest smile on my face, believe it or not, when you guys were inside the aircraft and actually interfacing with all the different parts of the digital cockpit and everything, because you can really picture yourself in the helicopter and getting ready to go flying in the aircraft. And I'm really looking forward to that. So thanks again, Jason. I know that you are incredibly busy. This takes a lot of time to be able to put this together, this AMA for everybody, but I know that it's so valuable and people really enjoy it and they really appreciate it. And so thank you again for taking the time. We've got a really great list of questions. For everybody that is just starting to connect now and haven't put your questions in, make sure you fill in your questions in the chat section, and we're going to post those to Jason right now. He's going to be able to answer those live. I think this is the only time that I can ever imagine in an aviation product launch where you have direct access to the founder and you can ask him questions live and he'll answer anything that you want. And so we're taking this opportunity here, and thanks again for that, Jason. So the first question is coming from that I saw in the YouTube comments about the gas outflow past the speed reduction gearbox and managing heat and flow. Is that a problem that needs to be managed, or is everything taken care of there?
It's a characteristic that needs to be managed. It's something that's been done fairly frequently in a bunch of engines over the years. So you do have to manage the heat flow very carefully. Some engines do it with an air gap and an airflow as part of the secondary air system. Other engines do it with heat shields, and some engines do it with a combination. So it is a done thing. You do have to manage the temperature in the gearbox very carefully, because the gearboxes are generally made from lightweight alloys with relatively low melting temperatures and relatively low operating temperature limits. So we have to be very careful about that, but we've got that. We're all over that. So it's all designed to operate at a temperature that it's capable of withstanding long term.
Super. So second question is Jason asking, Jason, if an operator completes the build school, does that allow them to do the 100-hour inspection, or does that still have to be done by the AAP?
I think local regulations would permit that in some territories, but it's our view that we will provide such a comprehensive package of maintenance support that you're better off just having your local A&P mechanic come and do the course that's included with the purchase of the aircraft, and then let a qualified mechanic look after the aircraft. HX50 is a fairly sophisticated helicopter, and so you're really better off benefiting from trained maintenance technicians to maintain it at the levels that it left our factory in. So we'd recommend that you take advantage of the inexpensive maintenance provision that we provide through your local technicians.
Okay, very good. Next question is from an early client as well, from Tony, and that's a fairly lengthy question, but I'll go through and read it. So for our VHF bandcom radios in the 117, so 117.975 to 137 megahertz range, the channel spacing has been changed in Europe. So the WF 01-01-18 to 8.33 kilohertz, requiring a third digit on the decimal side and the frequency and 2 extra frequency knob rotations. Not applicable on the keyboard entry. Compared to the original 25 kilohertz, so the rest of the world has zero appetite for following this change. So my question is, will the channel spacing on the comms radio be selected to 833 kilohertz or to the 25 kilohertz? So is as to be set according to the geographic location, or even a smart geolocating interface that will switch down to the 8.33 kilohertz spacing if flying in the European airspace?
Cool. So firstly, apologies, Tony. I should have answered this on the app a little while ago, and I haven't had chance to pick this up with Eric. My intention for this will be, it'll just be a line in the settings page on the IPI, so you can just switch from 833 to 25 kilohertz spacings as simple as any of the other settings. The one thing I haven't done yet is checked with Eric as to whether the current remote mount radio that we've got specified allows us to do that in software, or whether it requires some modification on the back of the box. That's why I haven't replied on the app yet, but I will do that tomorrow for you and reply formally. But my intention is that that's a feature we can handle in software, in which case we'll do it on the IPI, so you could do it as you pass from one territory to the next, and it can be done by the pilot.
Right, Graham Champion is asking the following. I wonder how you have arrived at 140 knots for cruise speed, as opposed, say, to 130 knots or 150 knots. Are there some unusual engineering demands or aerodynamic or power concerns that scale widely to cruise higher than 140 knots that are not seen going on from 130 to 140 knots? Also, what kind of top speed do you predict, if you're able to reveal that?
So we talked about this topic extensively in the very early Q&As and AMAs. Fundamentally, helicopter aerodynamics start to get really, really difficult at about 180 knots. That's when the nature of the complex airflow starts to excite all sorts of horrific vibration problems that are difficult to deal with, and the power demands of the rotor really starts to escalate. And if you look at the old papers and textbooks, if you do these performance calculations yourself, you'll find that by the time you get to sort of somewhere between 220 and 250 knots, you just hit a hard line where it's just not practical to make a conventional subsonic rotor go any faster. In terms of practical limits, traditional helicopters weren't really limited by their aerodynamics. They were limited by their drag and by the fact that the structural dynamic design of the rotors was never designed to cope with the rougher running conditions the faster and faster you go. So what we did when we designed HX50, because it was conceived as a Grand Tourer helicopter, we really wanted it to be able to comfortably and robustly cruise at 140 knots. Now, there are other helicopters that routinely operate at that sort of speed, the H125, the Augusta 109, and some other machines as well. So there's nothing scary there. But what you do need to do is you do need to make sure you get your drag down to a level where you don't need crazy amounts of power to get there. You need a rotor aerodynamic design that's specifically designed to cope with operation at those speeds, and that tends to mean evolving aerofoil profiles as you go down the blade. It helps to have a swept or tapered tip, thinner aerofoils at the tip section, carefully organized twist distributions, and then the rest of it is really about the structural dynamics of the rotor system and making sure all of that stuff that we talked about earlier is done really, really well. So we've done all of that because this helicopter was designed to robustly cruise at 140 knots and then beyond. And yes, all of the performance calculations that we have at the moment, and that's based on wind tunnel testing dating back to 2019, lots and lots of modern CFD analysis, lots and lots of comprehensive aeromechanical analysis and trim analysis and a bunch of other stuff, as well as comparisons with benchmark aircraft as well. All of our performance calculations say that we will cruise or be capable of cruising or dashing significantly faster than that, but it's important that we meet all these performance objectives. So all we're prepared to say at the moment that we will robustly cruise at 140 knots.
Very good. And Cornelia and Christoph have a follow-up question similar. So we have a question about the rotor head cover. So how to prevent air penetration from going into the cover during hover or in flight? Would a spoiler make a difference? And I think they posted that on the app as well.
They did. I was filming yesterday, so I haven't had a chance to reply yet. In hover, I don't think it really makes any material difference at all. That area around the root of the rotor is very messy aerodynamically anyway. In forward flight, it's not so much the rotation of the blades that you have to worry about, it's more the forward flight velocity driving air in between any gaps that you've got between the rotating cowlings and the root end of the blades and the rotating cowlings and the pylon. Now, this is one of those situations where helicopters are full of compromises and we're really living with the least worst solution. And so in terms of the donut to the pylon cowling, we're really just controlling gaps there to make sure we get the maximum benefit out of the pylon cowling. In terms of the donut to the root end of the blade, the composite root end of the blade has a cover that fares out into a sphere, and we have a concentric location for the flapping and feathering hinges and an outboard lag hinge, and that means that we can keep essentially a fairly tight sliding spherical surface seal on the root end of the rotor blade. So there's still gaps there. It's not a close fitting seal. We're not trying to keep it airtight. We're just really limiting leakages to maximize the drag reduction that we get. It's not perfect, but you're trading that off against the fact that everything up there is flexible. So the gearbox wants to move on the roof of the structure, and the pylon moves by a slightly different amount, and then of course all the blades are flapping, lagging and feathering all all at the same time. So we've got to be sensible about how tight we try and fare that, otherwise it's just going to knock and rub and tear itself to pieces very quickly. And so, as I say, we've taken as much of a drag reduction as we can while still being practical about the gaps we need to leave to allow the system to breathe and articulate well enough to be robust in service.
The hardest long-lasting material I used with the drill bits was cobalt. Nothing else compared to tungsten or carbide or titanium. Any possible application for that hard cobalt material, like transmission gears? Bit of a material question for somebody that works with these things.
Yeah, listen, we're always interested in stuff like that, and certainly in terms of one of a very significant production cost for us is the cost of tooling tips. So we use a lot of carbide even in development here at PC1. So anything that can help reduce that is really interesting. The magic, the strategy, the magic of our strategy and how we've produced this helicopter with such a large scope of technical undertaking is to minimize any technical risk that we take on in terms of new or novel features. So we're very cautious about using anything that hasn't got a proven track record in service in the aerospace world that we can point to as part of our qualification and approval strategy. So in terms of doing anything novel on the gear teeth or the bearing surfaces, I wouldn't be prepared to touch that at the moment, just because what I need is a pedigree of previous solutions to be able to say to the approval authorities, no, it's always been done like this and it works like this, and we analyze it and test it like that, and that will get us through the approvals process and into service and minimize the number of hold-ups in approval and minimize the number of unexpected surprises that we get when we enter service. So I'm always open-minded to learn. If there's a real benefit, we'd look at it and we'd look at how we can use it and we can develop it. But I think the gestation period for pushing anything like that out into a product would be relatively long even for us, because we don't need state-of-the-art to make a state-of-the-art GA aircraft. What we need is proven and cost-effective.
Very good. Do the blades need coating? I'm not heard if they'll be coated or not.
Coating in what sense? I'm not sure I understand the question. So
unfortunately, the question doesn't have more. I don't know if it's a rotor blade or the
turbine. Oh,
blades.
yeah, it'll be talking about turbine blades. So some turbine blades,
yeah.
some turbine components have thermal barrier coatings, or they have coatings to protect against erosion or hot corrosion. There are some coatings in some parts of the engine, yes. They're all proprietary coatings, and we use them where they're necessary. We try and avoid it as much as possible because it all adds cost. So, for example, at the moment we're not coating the combustor. If during the long-term testing we start to find that it needs it, it can be added later. But we're trying to do with the minimum we possibly can for the first test engines.
Right. Next one is, I believe transmission gears are treated and signed off to run without oil for 30 minutes. Is that right?
That's correct.
Okay.
It's part of the certification standard. So the way that you do that is the main purpose of the oil is to manage the heat at the gear teeth. And so with the way we design the gearboxes is so while the lubrication system is throwing oil around everywhere, there's lots of little catchers and reservoirs and slow leaky shelves and things like that. So even if you cracked your gearbox and completely instantaneously drained all the oil out of it, it would be dripping oil onto the critical mesh locations intermittently for quite a long while after you'd empty the gearbox casing. And so that, plus the residual oil in the system, plus the thermal mass of the system, limits the rate at which temperature builds up in the gearbox to a time where the materials can maintain their mechanical properties for long enough to give you the half hour to get back on the ground. So that's what we do there.
Okay, excellent. How many cycles of test, measure, redesign, and rebuild do you expect to have?
There's no easy answer to that. I'm sure there will be numerous details in both the engine and the aircraft that we look at and want to refine or improve. And the secret of all of this, and it was instilled in me by a very early mentor of mine, is you've got to know when it's just good enough. And so as soon as it meets the criteria for the performance that we've promised and the reliability that we need, we stop. Because a natural engineer would never stop refining. They'd keep going on and on and on and chasing perfection forever. So I expect we'll need a few iterations on a couple of difficult bits, but by and large, the strategy imposed by me will be stop as soon as it's good enough.
That's clear. All right, the next one is, what is the blade effective hinge offset or pitch link delta 3 angle?
It's about 3.5%. So it's very modest. There are some modern rotor heads. Obviously, your rigid ones, they go out to sort of 14-ish%. Your BO105s and things like that. I think the 105s is 17%, and they have crazy levels of agility. But the trade-off for that is the fact they have a very rough ride in turbulence, and they transmit a lot of vibration down to the fuselage. There's two characteristics that drive us to wanting to have a relatively modest hinge offset. One is the fact we've got a very high inertia rotor, so that multiplies up the centripetal acceleration, the centrifugal forces, and so a small hinge offset will give you a big control moment with a heavy rotor. And so we need to keep it low for that reason. And then the other reasons are more about packaging, trying to keep everything in that donut as small as possible, keep the donut as small as possible, and keep the response of the aircraft nice and benign in bumpy weather.
Nice. Sounds like a fun ride. Smooth. Can we get a little more detail on the combustor spray nozzles? Not clear if I have a two-stage nozzle or if the strategy has changed to two separate nozzles.
The strategy remains that the production engines will have a dual orifice nozzle. And the reason why that's the best approach for us is that if you go to simplex nozzles, which is the simplest way to do it, starting the engine becomes really difficult because you can't have a wide enough range in fuel pressures to be able to just vary the fuel by the factor of 10 or 12 that you need from ignition all the way up to maximum power. And so you end up having to bring on the fuel nozzles in groups of 4 and then another 2 and then the remainder, which gives you the need to start modulating your fuel pressure up and down all over the place. It makes a real mess of your air-fuel ratios around the combustor liner as well, because you've got all the engine's fuel going in through 4 nozzles, but the air being delivered through 12. And so it gets really complicated. We've left the door open for simplex nozzles just to help us get through some early tests. But the production engines will all use the dual orifice nozzles that you've seen.
Clint Pulver. Hi, Clint. Good to have you. He's asking, can you make the paint scheme on top of the blade black and white or red and white instead of white and yellow?
Yeah.
Will that be an owner switch option, or is there a reason for yellow and white versus other colors?
The reason for yellow and white is Mark came up to me on a Monday morning and said, what colour do you want the blades painting? We're painting them at 10 o'clock this morning. And I looked around at some other helicopters and thought, we'll do it like that. So no, with the paint scheme for the conspicuity will be designed along with the other paint schemes that we offer. So we'll make it look as Gucci as we can. We're limited. Well, we're not limited. It's good practice to keep the colours as light as possible because it'll keep the blades as cool as possible when they're in really hot parts of the world like Florida or Dubai and places like that. So the darker colours that absorb more heat are not a good idea. So with a composite blade, that is. So it will have to be fairly light colours, but I think I can do a better job of the paint scheme given more than an hour to design it.
They were nice. They were looking nice. It's great to know that anybody can do what they want.
I mean, they were looking shiny. It was nice. Basic question: when will you put all of the samples and components together, and when will the helicopter start flying? Is April 2026 deadline still current for the engine run? This is a key issue. This roadmap keeps getting pushed back.
Yeah, so we're on schedule at the moment to have all of the components we need for that first engine run here by the end of April. So as in built, all of the bits and pieces that come in from outside suppliers, high temperature seals, igniters, exciters, things like that, that will all be here in time, and we will build it at that point. So yes, we'll have all the bits by the end of April, and then as soon as we've got all the bits, we'll build the engine, stick it on the test rig and run it. So I fully expect to run that engine as early in May as we possibly can.
And then that puts us on track for a flight test when?
End of the year. So my personal target still remains, I think I said the 17th of December, because the work's due is on the 18th. So yeah, so 17th of December is the target for first flight.
Excellent. Gyrocopter Girl is asking a very particular nice question. The R66 has a huge range with the cycle movement, and therefore it gives me the possibility to land on slopes versus the C145 3D with 5 blades. That can't land at on the same places. What's the approach for the HX50?
So at the moment, the slope limits are 10 degrees, and that's limited by your cyclic range. I think in machines like the early H145s that had the BO105 rotor head, it was more to do with mast moments. So with LARD, because that has such a stiff rotor system, the benefit being you have huge control authority. The moment the rotor disc is at a significant angle to the rotor mast, it puts huge bending moments into the mast and then into the gearbox. So I think that's more about the trade-off with those early rotor heads that were very, very, very stiff. So our slope landing angles are very much in line with the majority of the other helicopters that you'll find out there. So 10 degrees laterally is pretty standard. 10 degrees nose up is pretty standard too.
Okay. Yeah, beyond that, it starts getting a little bit sketchy anyways. So. Did you, next question is, did you use Shaw's CFD transition method for airfoil characteristics or wind tunnel 2D airfoil data? Is this good enough for span-wise flow?
So we did the data that we use for all of the performance predictions is all empirical. We don't really rely on CFD for rotor aerodynamics. We've done a fair amount of CFD on the tail rotor, but that's really because CFD is the only practical way from a standing start that you can look at the rotor and duct interactions. But for the main rotor, that's all done with wind tunnel data from really reliable sources that we've then used in conventional comprehensive aeromechanics codes and performance codes. So a very, very conventional, traditional way of doing it. And the aerodynamic design of that main rotor up there is not very clever. There's lots of examples of people doing it in very similar ways out there, so I'm not expecting any real surprises out there.
Connor pays a lot of attention to the update, and he has a detailed question.
Good.
I caught a glimpse of a Raspberry Pi CM4, which was on display at the avionics board. How does the team approach the trade-off between choosing commercial off-the-shelf tech versus DIY?
I don't think you saw that on an avionics board. I think you probably saw that on the combustion rig, which is just over there. So for some of the test rigs and things like that, we use the simplest, quickest, easiest ways to get test equipment up and running, because if you're not careful, you can spend longer designing test rigs than actually designing the bits that you want. So we use a mixture of PLC controllers from Siemens, Raspberry Pi, we've got some Arduino stuff and various other bits and pieces just to pull test rigs and test equipment together. The avionics stuff is much more carefully controlled. So the avionics board are all aerospace grade components, aerospace grade boards. The microcontroller stuff is all running bare metal as you'd expect to get the integrity levels that we need. But it is commercial off-the-shelf boards and equipment we're using, but it's the aerospace grade stuff that goes into the primary flight display and digi-cockpit controllers, the autopilot and flight control computer, the FADEC, and the various other critical systems on the aircraft. There's no shortcuts there at all.
Very good. What happens if the screens fail? Are there a backup of the primary instruments?
So if the screens, both of the primary screens are totally independent and redundant. So they have their own power supply, they have their own display board processors, and they have their own connections to all of the peripherals on the avionics loom. So if you lost a display, you'd simply use the other one. You've got not just a handful of reversionary instruments, you've got a full suite of reversionary instruments fitted as standard to everything else. And remember, most of the stuff that's in there displays information rather than controlling it. You can control pretty much all of the functions that you want from the IPI or either of the screens, so you've got lots of redundancy there. Sorry, there's another important point that I've said before, but I'll repeat for clarity. Remember that things like the governor and the FADEC is totally separate from all of those systems. It's a sandboxed microcontroller system that's dual redundant in its own right, and is only connected to that system from a control point of view from a single fly idle switch and there's fail-safe design into that as well. So it's a very robust architecture.
Very good. Next question, I can answer the first part, and you can answer the second part, Jason. First one is easy. How many orders do you have right now? So right now, today, we have 1,440 orders from 78 countries. And I take this opportunity to also make an announcement and make sure that everybody knows. Probably some people have here in this AMA their first contact, or they have come to several AMAs, but they have not attended a presentation that Mischa and I, we do every single day. Now, in that presentation, we go over a lot of different things. And there is a very special offer that we provide to anybody that comes and attends the presentation that is worth it. Big reward. I can assure you that you won't regret it. And it's about 30 minutes. So if you want to come and know exactly where we are standing at this point and what's coming next and what is the opportunity to order that craft, go to our website, enroll in the presentation. You're going to like it. I guarantee you this. And Mischa and I will be live there. And you also take questions, especially commercial questions you might have. This is more technical AMA. But if you're interested to order the aircraft, enroll today. And you're going to like what you're going to see specifically at the end of the presentation. So the next one for you, Jason, is what is the production capacity? What's the volume that you're planning? Because there's so many orders, right? So what are you planning to really fulfill this incredible demand that hasn't stopped yet?
So the next phase of development, as soon as first flight's out the way, is we will be breaking ground on the World Production Centre, which is a bigger version of what we're sat in here now. And that's designed to produce 1,000 HX50s, HC50s per year. It'll produce 500 in year one, then ramping up to 1,000 in year two. And then as we expand out to additional products, then we'll add further production capacity as we want. But 1,000 per year is the intended production volume for the HC50 series.
Yeah. Is there any plan for having voice command control?
It's not something we've looked at the moment. No, at the moment there's nothing. It's not something that we've looked at.
Okay, next one is great work, Jason and team. I understand that the current focus is on getting to the first flight and then production. Could you please share a timeline that is the estimate for the utility version?
When you say the utility version, you're really talking about HC, the HC50, the commercial version. The way we've presented HX50 to date has been very much focused on a trim level that suits private owners, so lots of leather, lots of bells and whistles. The standard HC50 version will be available with a much more stripped out utilitarian interior, so that'll be part of what's offered when HC50 goes into production. So the HC50 approvals are really just expected 2 years following the HX50 approval. So that would put it about 4 years from now, starting production.
Okay. Very good. And avionics question: is there an audible altitude countdown for landing?
No, there isn't at the moment. So we're open-minded to that sort of stuff, and it's not a difficult thing for us to do. But one of the things that I've disliked over the years is you can get into some aircraft where they've got lots of disparate avionics fitted, and there's bings and bongs and call-outs and things for all sorts of things. And what happens is the first thing you do when you're a pilot is get in and turn all that stuff off. And so we wanted a really simple, unified and coherent user experience. And we're leaning heavily into haptics, so you've got your haptic power management on the collective, and you've got envelope protection through haptics on all of the controls. So other than the rotor overspeed warning, we're trying to avoid audible warnings, because I think it's just going to confuse the user landscape. But when we start testing and when we get some real pilots in HX50, then we'll keep a watching eye on that. And if we think there's a real case for doing that, then we'll look at it. The system allows us to do it, but we haven't done it yet.
Thank you, Jason.
Is it safe
I definitely appreciate that. Yeah, sorry to cut you off there, Ruben, but there's nothing that I dislike more than hopping in a helicopter and I go flying and you just get a bing and a bong and this and that from every notification that's coming through. And I find it quite distracting, actually, and you start to tune those things out. And like you say, if you have the option to turn it off, you typically do turn it off, because for the most part, they're more distracting than they are beneficial, from my opinion anyways. So.
Yeah, my favorite was always the terrain warning, because all the terrain databases are based on aeroplane fit-outs with aeroplanes landing at airports. So when I try and land in my back garden, every time I land in my back garden, I've got this system shouting at me, terrain, terrain, terrain. And my sister-in-law's quite a nervous flyer, so she'd be panicking. So turn that off every time I get in.
Doesn't make any sense to have terrain in helicopters. It's always terrain around you.
That's the point of it.
Hope so. That's the point.
All right, next one. Is it safe to assume that demisting uses natural pushed air and not dependent on a fan?
You've got both options. So there's a natural ventilation system in the aircraft, because that's part of the implied certification requirements. But we also have a full forced air demisting system that goes through a dehumidifier as part of the climate control system. So it's very robust demisting, as you'd expect in a modern car.
Nice. And Thomas is asking, how is the progress on the factory? Arguably the hardest part of the development.
It's not the hardest part of the development when you've already built 4 of them. So we've just built PC1 here, which has got almost everything we need for series production. So the only thing that we're missing here is the line itself. And so we need to complete the development of the engine and the aircraft so that we've physically made every component and assembled every component to have the data to put the finishing touches to how we want PC2 or the Global Production Center to work. And then we will just take a rented building, there's one a mile that way, and implement that while we're going through the approvals process.
All right. Now, next one is a personal question. You know what? This personal question, it seems it's not important, but it's really important. It's really important because we have covered this in the podcasts that Mischa and I have been doing with you. And I highly recommend if you check out the Hill Helicopters YouTube channel, by the way. I think we have more than 200 videos there. We tell the story of in and out. We tell the story of every single part of this helicopter, and also the journey, the experience, and how Jason has gone through the project, his enthusiasm, his background, everything. So next one is related to that, Jason. It says, personal question, if I may. How are you holding up energy levels on this marathon project? And this is important because sometimes people ask us, what is the risk of this project? Yeah. And we say, Jason is a key man. So how is he holding?
I'm holding together remarkably well because this is my dreams come true. Being given the opportunity by all of these customers to develop this helicopter is really a dream come true for me. So yeah, it's really, really hard every day. I laugh with my wife sometimes. Sometimes it can take me till 4:30 or 5 o'clock to make it to my office. Because I just come in and wade through one problem after another before I can make it to my office, and that's obviously demanding technically and personally, and running a program like this is demanding technically and personally. But we're now in a very privileged position that we've got an utterly world-class team, an utterly incredible team of people around me that are just on their A game the whole time. So it's easier than it's ever been to get stuff done around here because we've got capable people that can do it. We've got a very positive and motivated team here that love what they're doing. They recognize the opportunity that we've been given, and so the team is in a better position than ever to sort of maintain morale, and everybody can see the finish line now, so everybody's excited about that. And so it's demanding, but it's a privilege rather than a burden to do this. So we all have a great time doing what we're doing. We're so excited about getting this engine running, and we're so excited about first flight. And we know there's a load of work after that, we all recognize that, but getting to that milestone, having delivered what we set out to deliver all those years ago, is such a motivating thing to continue to strive for. That, yeah, we're having the time of our lives. So it's hard, but it's great. I'll be ready for a holiday once it's flown.
This reminds me, before you go to the next one, Mischa, because this reminds me of something I read last year, and it really applies here. It says that the stress that kills is when you have a challenge that you can't solve. That's what really erodes. That's the bad stress. But the stress actually that is good is the one that you apply energy that with very hard work. And we did talk about that on the podcast. We like difficult things. You like difficult things. And we know it's difficult, but we know it's possible. So that stress actually enhances your capacity. So I know you very well. We've been working for years now. And I know that exactly what you said. When you did mention the enthusiasm that really drives this whole project, that's the key.
And I tell you another, I tell you another thing that's really motivating for everybody involved now as well. It's when you look back and you see how far you've come. If I don't know if it's the podcast. I think it was one of the earlier videos we did. You look back at when we started in a tiny little office with just a couple of us. And then you look at where we've got to now, and the capability of what we've designed and what we've built, and that's hugely motivating because you're just doing what you said you were going to do, and success breeds success. So the more of it you do, the easier it becomes to do more, and so you just keep going, and this will continue to accelerate. So we've said many times before that the 50 series is really just the start. It's the entry-level product for the platform that we've built, and there's bigger helicopters and there's fixed-wing aircraft coming all off the engine, the avionics, the structures, the drivetrains that we've built, and that's such an exciting future to look forward to. But right now we're diligently just focusing on job one, get this one over the line, get it into production, make everybody happy, and then go again with the next fun project.
Amazing. It's an exciting future for sure. Spencer is asking, have you considered offering premium non-leather interior options? So many luxury automobiles like Tesla, BMW, and Mercedes-Benz are moving towards advanced synthetic materials that are more durable.
Yeah, we've considered it, and we will do it. We haven't done anything about it yet. Those are kind of nice to have things from a development point of view. The big push on the seat has been to get a seat that has all the functionality that we need. It's comfortable, it's crash worthy, we can make it the way we want to, we can trim it the way we want to, it looks right in the cabin, and all of those things, and we're there with that now. We're building 10 of the prototype seats at the moment. I was going to include it today, but we just ran out of time. So we'll show you those once we've finished building them. And they're trimmed in leather at the moment because the launch customers, by and large, will tend to want leather seats and leather interiors. But there's nothing stopping us doing that in automotive fabrics, as long as it passes the flame retardancy and other approval requirements, or other fabrics and leather alternatives. Totally open-minded to that. I think the man-made fabrics and leather alternatives are actually lighter. And one of the horrible things that you find about making a comfortable seat is that the foam's really heavy and the leather's really heavy, and then if you want to cover both sides of it, it gets really, really, really heavy, so nothing's free. So those sorts of things are nice options, particularly for the commercial variants.
Nice.
How much time will it take to certify the aircraft in the US, UK, Canada, European Union? Pretty much everything in the helicopter is bespoke. So I just wonder, what's the time frame? What I'm seeing, what is the time frame? Seeing how it takes 1 or 2 years.
It's the same time frame that everybody else works with. So the total certification time frame is sort of 3 to 5 year program, from when you first start through all the way to being in production, and you run that in parallel with the different authorities. So we'll keep the UK one a little bit ahead, so we're not having to so we've got a stable basis that we roll out into the different countries. Then we only have to pick up the differences between territories, but it's the same time scale as everybody else. The fact you've got the main thing to bear in mind is that we've got 2 certification programs. You've got the aircraft and the engine, but they run in parallel as well. These things don't stack end to end, they run in parallel. And the fact that we're making stuff doesn't really make it any more difficult. It doesn't change the tests that you have to do. It's just you have to do them. And sometimes doing stuff when you've got control over it is a lot faster than negotiating with a lumbering aerospace corporation over getting them to provide the documentation and the support you need to validate their bits that go into your aircraft. So I don't see having made all the stuff ourselves as being in any way disadvantageous. I think it'll expedite, if anything. The fact that we've got to do the engine is clearly a big additional piece of work, but it will run in parallel.
All right. And the next question is, when will maintenance training be available?
It'll coincide with the start of the deliveries of the first machines. I don't think it's realistic to say that we'd be able to do it any sooner than that. I think there's a significant amount of work to do to get PC2 up and running in a very tight window. So the earliest the people that need to be involved would have headspace to deal with that will be on the immediate run up to the first machines going into production.
Yeah. Okay.
Excellent.
Very good.
All right, we're reaching now almost 2 hours since we started. Just to give you also an estimate and how it's worth sticking around, because we only have another 10 minutes. So if you want to hear the full spec of questions, just hold on another 2 or 10 minutes. We'll be able to get to the end. And we appreciate almost 2,000 people have connected. That's amazing. Always incredible high numbers and a lot of interest from all over the world. And right now we almost have almost 500 people connected. So great to have you. Stick around. It's going to be worth it. And then 10 minutes we'll be closing. Next question is, will the blades have a TKS fluid or an inflatable boot?
TKS fluid or an...
I don't know what it is.
As in de-icing?
Oh yeah, must be probably.
Oh yeah.
TTK,
Yeah, that would be for de-icing. Yeah.
The aircraft is not cleared for flight in icing conditions, so there's no de-icing provision on the blades at all at the moment.
Yeah. All right. And the next question is, Is it sold as SKD or complete example delivery to South Africa?
All aircraft are delivered ex-works in the UK, so the customer is responsible for their own export, but the aircraft would be completed and test flown here and then disassembled and crated for easy shipment by whoever your chosen freight partner is, and we can provide some advice on who the reliable ones are that we've worked with before.
Excellent. Before next question, I do have a comment and I have a request for everybody. Actually, I forgot in the last bit there. We have all these people connected, and it really helps if you like and appreciate, you're a fan of helicopters, hit the like, because that helps us a lot, and we want to make this available for more people. So you can just hit the like, it'll help us a lot. Of these 400 people connected, that'll be great. Next one, how hard will it be to fold the blades? How much time will it take?
It won't take very long. You can climb up onto the top of the aircraft, pop the folding pin out and then swing them round, or do it equally easily from a step ladder. So a few minutes. I'm going to qualify that though. If you're in a position to buy a personal helicopter, build a bigger shed and have a big enough hangar so you don't have to fold the blades, because anything that adds friction to going flying when you've got your own helicopter at home will make you more likely to not go, or to choose to go by car, or to think, oh, I can't be bothered. So just, if you're thinking about building a hangar, build a hangar that's big enough so that you can just roll it in and out and go. Don't skimp on hangars. Hangars are trivially inexpensive compared to helicopters, so just build a decent hangar.
Yeah, I fully agree. Unless you're in a position where you already have a two-bladed helicopter and you have a narrow hangar, or you're going to be traveling somewhere and you need to put it into a narrow space, yeah, definitely use the blade fold only when it's necessary.
Yeah. It's less of an issue for the guys that share airport hangars near the big cities and things, because the ground crew can do it for them. But certainly as a private owner landing at home or at work or something like that, you don't want to be messing about with blade fold every time you go flying. You just get a bigger door.
Exactly. That 10-15 minutes is not a big deal, but when you do it every day, it starts to add up. Yeah. The next question is from Robin. He's asking if the bird ended. There is still actually a substantial discount available, and if you want to find out what it is, like Ruben said earlier, we'd highly encourage you to attend one of our daily presentations. Easy to register for that. You can jump on the Hill Helicopters website, say that you're interested in booking a presentation, pick a date that works for you. We have them every day, and we're going to be happy to share with you what that discount is. It is quite substantial still, and it has been decreasing over time, and that's something that's so valuable to the customers, because their position actually continues to gain in value over time. The discount was actually much larger in the beginning. The first 100 had a very substantial discount, and that has been decreasing over time. But right now, we still have a great opportunity for anybody that's wanting to become an owner, and there actually isn't a better time. We've seen as the program has continued that there's major spikes at different milestones along the project, and right now we're getting very close to that first engine running. We know that there's thousands of people in the pipeline that are waiting for different milestones to happen. That first engine run is going to be one with a pretty big substantial spike, which obviously increases the wait time, because those serial numbers continue to increase. Same thing happens with the first test flight. There's going to be another huge spike there, and so there really isn't a better time to be able to secure an early spot and still get a really good discount. So you have that available. I'll go right on to the next question as well then. When you have the first engine running, at that moment, how many prototype engines will you have ready that you can begin the next steps? So is it just the one that you're going to be having, or are you shooting for 3, for example?
So we've generally built around 5 sets of components of everything for the engines. Now, not all of those components make it to the end of the process. We sometimes scrap some of those off while we're perfecting the manufacturing processes. So I think Mark's latest estimates is we'll probably have enough components to make the first 3 engines ready at the end of April, and some of those components will keep in part machine states, so that if we want to tweak things, we can tweak things and you've got most of the work done, ready to go. So it's not like if we have to modify things, you go back to the beginning again and you've got a long wait to recreate things. And it's not like if we damage an engine, which is quite possible in early testing while we're exploring its envelope, that we're back to a long wait to rebuild a prototype again. We've got parts in stock, as we will continue to have throughout our operation, so that we can support our sort of development and then operational needs. So have in mind we've got three engines worth of parts available at the moment.
It's a continuous snowball, right? So obviously you can continuously be making parts in the background that will be ready as you're making changes and progressions as well. So it won't be starting from scratch again, like you say, when you want to start
making the first one of any of these components is extremely slow and extremely time consuming, because you've got to lay out the entire production routing, develop each stage of those processes, get every little part of that to work. Once you've got that mapped out, doing it again, as long as it's stuff that we do here, we can do really quickly. If it's stuff that has to go out, then there are lead times that we can't control. We don't do some of the heat treatment processes and things like that here yet, but the vast majority of all of the manufacturing in that engine is done here. So we've got great control, and all of those processes are mapped out now, so we can produce components pretty quickly.
What is the plan for training when delivery begins? I work for a serious training center, and there's a great deal that goes into after-sales training, flight training. Your customers will be similar to ours.
Yeah, absolutely. So in the very first instance, as we're sort of ramping up production and building the early machines, then we'll be doing a lot of the early training here, because there simply won't be enough trained instructors and examiners with the various tickets around the world. So we'll have a core group of instructors and examiners here that can support on our, what we call the 0 series, the initial machines that we produce into our own fleet before we start making customers' machines. And so we'll handle that here, and we'll use those machines and those training courses to train as many examiners and instructors as we possibly can, some that come with customers and some that are just third-party organisations that will provide part of the support and maintenance network out there in the field. So there'll be an aggressive ramp-up of training people to support these machines out in the field as soon as we have our fleet of machines here to start doing that. Sorry, there's one more point to add to that as well. Each machine is obviously sold with a 5-hour type rating and a safety course. So we're providing a very comprehensive training to each owner while they're with us when they come to build their machine. So they'll leave fully trained from both a safety perspective and from an operational perspective. And then again, as we grow, we'll push more of that out into the existing service and supply chain.
Very good. All right. Ruben, you want to ask the next one? Or no, as you see, you asked the last one. In your professional opinion, would a charcoal fuel furnace represent the optimum solution in terms of its resistance to the elements?
I don't really understand that question. Read that one to me again.
In your professional opinion, would a charcoal fuel furnace represent the optimum solution in terms of its resistance to the elements? I'm not sure what it's referring to.
I'd need a little bit more detail to understand that. I don't understand the context of that question. If the person wants to write in, I'll answer it for you, but I don't know what context he's asking about.
Great. Okay, you can send an email to the...
Yeah, next one is from Eric. Is the approval process developing according to plan?
Yes, it is. We are the bottleneck at the moment. We need to get these bits finished and on the test bench, and then we can push ahead with the next steps with the authorities. So the authorities have been super supportive. They're driving us, so we couldn't ask for a more responsive domestic authority. So the ball is very much in our court at the moment. We need to get these bits done, and then we can push through the approvals nice and quickly.
Great. A question on the GT50 power. I see that it is a single-spool turbine rather than a two-stage turbine, unlike the Rolls-Royce engines I have been familiar with. How quick is the response on single?
That's not correct. It's a two-spool engine. So the gas generator is a single shaft. The power turbine is a separate shaft in the behind the gas gen section. So it works in exactly the same way. The responsiveness, if you're used to the older Rolls-Royce engines, is in some part dominated by the hydromechanical fuel control system. The FADEC system allows us to make the engine a little bit more responsive, but obviously you're fundamentally limited in ramp up and ramp down rates by compressor surge and stall.
And that's Matt, who has a Bell 407. So.
Okay, yeah. No, it's a dual. It's a dual hour mat, 100 club mat.
Mm-hmm.
Yeah, it's a two shaft
yes.
It's a two shaft engine mat, but the power turbine shaft comes out the back, not through the center of the engine. It'll feel very much the same, just a little bit more responsive.
All right, next one is from Robin. Comparing turbines in helicopters, what is the GT50 fuel burn rate per hour at 400 horsepower compared to other turbine engines when producing 400 horsepower? Is the GT50 a step up in efficiency or similar to other competitors?
It's similar. It's at 400 horsepower. It's about 35 US gallons an hour. So it's basically a 25% thermally efficient engine, the same as most of your other uncooled engines. We're at the limit of how hot you can push these materials before you have to cool them. Cooling's very difficult, complicated and expensive at this scale. So you're at some hard thermodynamic and metallurgical limits. So it's as good as the others, but it's no better. The USP about the engine is the fact that it lasts a long time and it's inexpensive.
It's a super boring, efficient, low-cost engine.
Yeah.
Yeah, very good. Can you talk about the air inlet? About the inlet air filter for the GT50, given its tight tolerances?
It's just a conventional inlet barrier filter. So much the same as you'd see on a 505. Slightly different geometry because it's buried in the airframe in a different place. But it's just a conventional inlet barrier filter.
Do you believe that you will be possible? Oh, sorry. Do you believe that you would possibly be much further advanced in your engine development if you had partnered with a heli engine manufacturer? No,
absolutely not. I think we'd be much further behind. Why would they help me?
Waiting.
Why would they help me? If you
sabotaging the project and waiting and putting you in the
if I could have just gone and stolen the team from the 1950s that did the Allison engine, or the team that pioneered some of the Safran engines, then absolutely we could have done it faster than having to piece together a team from all over the place to do it. But fundamentally, a lot of the real knowledge in developing an engine from scratch has died with the last people that did it. And people forget how long it's been since a new engine in this size class was done from scratch. And so there are lots of people out there and our team has been pulled from other engine manufacturers with lots of relevant experience, but you can't easily reproduce the experience of the small teams of people that did those very early engines from scratch. That has to be learnt the hard way, I'm afraid, and that becomes one of our USPs, doesn't it? We now have the ability to do this, not just to design it, but to manufacture it and to modify it and adapt it to different applications. That's been very hard won, but it will serve us very well for the next 20 to 30 years.
Very good. And where will you be doing your high and hot flight testing?
I haven't decided yet, to be honest. There's some places in Spain and there's some places in the US that are potentially suitable for us, but we've done nothing to plan that yet. As I say, at the moment, everything's about the functional day job of making components, getting them proved out on test rigs here, and then getting the very early test flights out of the way. and then we'll have a fairly extensive low-level test program to go through to do load surveys and all the other good stuff you have to do before that becomes an issue.
All right, the last 3 questions, and we'll be closing after these 3. Next one is, has there been any thought towards incorporating advanced sensors like LiDAR, which would alert pilots towards hard-to-see cables in light of the slackline strike in Arizona?
Yeah, I am really interested in that sort of stuff. We haven't done anything about it yet because obviously we've got quite a lot on our plate at the moment. But I think anything that helps situational awareness, anything that can improve pilot hazard perception is a good thing. And I think, as we've demonstrated with the DigiCockpit, we're very much in favour of reducing pilot workload, letting the system do as much work as it can to make flying easier and safer and more enjoyable. And so that sort of stuff is interesting to me. I just have to balance that with allowing the complexity of the aircraft to get so high that it starts to become operationally unreliable, and little sensors failing here and there just become a maintenance headache. And the other issue you have to balance is, if you're going to get a pilot to rely on the capability of a sensor spotting wires or hazards, then they can become complacent. And it's a difficult balancing act between whether you make it really clear that looking out the window and not flying into anything is your problem, and the system will, the aircraft system will just make sure that if anything important stops working, it tells you about it, or all of a sudden it becomes the aircraft that's flying itself, and then it's responsible for flying. And so there's a number of different issues that need to be resolved there to decide whether that's the right thing for a VFR aircraft.
Okay.
Very good.
Sounds
Mischa,
good.
you know what? You could do the last question probably, because I think the next one is good to finish and close with that one. So you can go with the last one probably.
Yeah, so sounds good. We'll just go with who will make the
45.
FADEC and the other primary engine components?
We'll make that.
Okay.
If it's if it's important, it's made by us. Well, in fairness, pretty much everything's made by us, but certainly the important things have to be made by us.
Very good. Excellent. The next one is probably going to be a repeat, but it's good to close this one because this AMA, I think, was all about how we're going to close this session with this last question. And by the way, thank you everybody for your attendance. We had incredible interest today. Another very close to a record, almost 2,000 people connected today, and a lot sticking to the end. So we really appreciate that. Thank you for all the likes. We had a lot of likes after that ask. We really appreciate that. That helps us. You're a fan of HIL. You want to see this succeed, and it's getting so close to big milestones. And what the best way to close this session, to remind people, it's a question. I chose to ask Mischa to switch questions because I think this one closed really well. Jason, remind us when you're going to see this engine running and what is your aim for the first flight. And then you can wrap it up and we'll be closing the session right after. Thank you very much, Jason, today. Another great session.
Thank you, guys. So as we stand here today, we will have all of the components ready for the first engine run by the end of April. We will then assemble it and run it as early in May as we possibly can. And then, assuming the engine development goes well, my intention is to get 3 wheels off the ground by the 17th of December this year. Thanks for your time, thanks for your attention, and we'll speak to you next time.